Great. So last time we started talking about convergence, probabilistic convergence, or in other words, limit theorems. And we started by talking about convergence in probability. We defined the Markov inequality and proved the Markov inequality and the Chebyshev inequality, which derives from that. And here is an example for proving convergence of a probabilistic sequence, namely convergence in probability. In proving convergence in probability, we often use Chebyshev's inequality. So here's the problem. Flip a fair coin n times independently. Fair coin, so the probability of getting heads in each toss is 1/2. Let y sub n be equal to the number of heads minus n over 2. Does yn over n converge? So first let's think about yn itself. What is yn? Yn is the number of heads in n tosses. So we could model it as the sum of n IID Bernoulli random variables, such that xi is 1 with probability 1/2 and 0 with probability 1/2. Right? Why? Because xi is 1 if I get heads and 0 otherwise. This is standard. We've done this before many times, in fact. So what is the expectation of yn? It's n times the expected value of x sub I or x sub 1. The expectation of one of these Bernoulli random variables is p, which is 1/2. So it's n over 2. So the question asks us to think about, actually the question, let's define this as y tilde. Sorry, the question defines yn as the number of heads minus n over 2. Okay? So this is a number of heads. This is the number of heads minus n over 2. I from 1 to n. So what is the expectation of yn? Expectation of yn. Expectation of the first part is n over 2. So it's n over 2 minus n over 2, which is 0. Okay, so we're talking about a sequence of random variables indexed by n. They go like y1, y2, y3, and so on up to infinity. And their expectations always stay at 0. Okay? Nothing's happening to the expectation. Let's see what happens to the variance. Variance of yn. The variance of yn. This constant term, n over 2, has no effect on the variance. So it's enough to compute the variance of yn tilde, which is this first term. Now the xi's are independent, so the variance of the sum of xi's is the sum of the variances. It's the sum of the variances of xi's. The variance of xi for every I is equal to p times 1 minus p. In this case, p is 1 over 2, so we have 1 over 4. So the variance of the sum is, variance of the sum minus its mean is equal to n times 1 over 4, which is n over 4. So what's happening to the variance as the index n grows? The variance of this random variable is growing. Do you think the number of heads minus n over 2 is converging to something? Doesn't really appear to be converging, right? Because its variance is growing and growing to infinity. So it's not really converging to anything. Let's, on the other hand, think about normalizing yn by n, or dividing yn by n. What do we have in this case? Yn over n is 1 over n summation xi, I from 1 to n, minus 1/2. Right? So what happens to the mean and variance of yn over n? First of all, yn over n is like a sample mean for the random variables xi, right? So as I grows, we are adding more and more. That is actually as n grows, we're averaging more and more independent xi's. This is like a sample average, except we took the mean out. Let's compute the expectation. What is the expectation of yn over n? Clearly 0, because the expectation of yn itself was 0. What is the variance of yn over n? Well, this 1/2 has no effect on the variance. So it's really the variance of the first term. Variance of yn over n is equal to the variance of the sample average of the xi's. Now, when we multiply something by a constant, the variance is scaled by the square of that constant. So this is 1 over n squared times n times the variance of x1. Does everyone agree? This is an important step. So the variance of the sample average, 1 over n summation xi, is 1 over n squared times n times variance x1. Is everybody cool with this? No? We have n terms here. They are all independent. When we're summing n terms and taking the variance of the sum, it's the sum of the variances. Why? Because they are independent. Okay? I put here x1 because they are all IID. x1, it could have been x2. I just need to put a number here because I don't have the index I anymore. You see? So it doesn't matter what index I put here. The variances of x1, x2, x3, they're all the same. Okay? But I is an index that lives inside this summation, so I can't use I. Okay. Yes, please. We are right now, we're talking about a particular n. Right now, we're for a particular n. Well, this whole thing will be a function of n, and then we'll think about taking n to infinity, increasing n, just like we did here. For example, so the yn, the variance of the nth summation, say, is n over 4, and as n is taken to infinity, this will grow. But in this case, let's compute this. What will happen to this? This is n over 1 over 4n. Okay, so the variance of yn over n is getting smaller as n increases. This is going to 0. Right? So, okay, let's sort of summarize what we're trying to do. So far, it was just an analysis of yn over n. We haven't really answered the question yet, but we've analyzed the situation. We believe, based on this, that yn over n will converge. What do you think? Yn over n is something, it's the sample mean, whose mean is always 0, whose variance is going down to 0. So maybe it will converge to something. Maybe it will converge to 0. Now here's my hypothesis. I claim that yn over n goes in probability, converges in probability to 0. This is my claim. Okay, now I need to prove this. Let's remember what it means to converge in probability. Okay, let's refresh our mind from last time. Now, Yn converges to a number A in probability if and only if the probability that Yn over n minus A is bigger than epsilon is okay, the limit as n goes to infinity, this probability is 0 for all positive epsilon. Okay? In other words, the difference of Yn over n, our sequence, and this particular number that we think it converges to, goes to 0. In what sense? The probability that the difference is bigger than some epsilon is decaying to 0. Okay, this is the definition of convergence in probability. Okay? Essentially, the probability that Yn over n is far from A is going to 0. This means Yn over n converges to A in probability. So let's show that Yn over n in our example converges to 0. What is 0? 0 is the mean of Yn over n. Okay, so it's sort of intuitive that it will converge to its mean. Sequences don't always converge to their mean, but in this case, it's quite intuitive. Okay, let's see. What is the probability? What is A in our case? For our example, A is 0. Okay, so we need to compute the probability that Yn over n minus 0 is bigger than a positive number epsilon. Let's compute this. It's not that hard, maybe. Maybe computing this exactly is hard. Why? Because Yn over n is a sample mean. It involves n Bernoulli random variables. It's a huge binomial. Computing this exactly is hard. But what do we have? We have an inequality. We can bound this, upper bound this, using the Chebyshev inequality. Okay? In particular, remember the Chebyshev inequality. So these are two reminders. This is reminder 1, definition of improbability convergence. Let's remind ourselves Chebyshev's inequality. What is that? The probability that the random variable x minus its mean is bigger than some value epsilon is upper bounded by variance of x divided by epsilon squared. Okay? Here mu is the expectation of x. Is this true for any random variable x or only for positive random variables? It's true for any random variable x with a finite mean and variance. Okay? So let's apply Chebyshev's inequality to this example. Okay? How do we do that? Here we have the expectation of Yn over n. Okay? So it's exactly in this form. Here, x corresponds to Yn over n. Mu corresponds to 0. Epsilon corresponds to epsilon. Okay? If you want, do this. Right now it doesn't really, epsilon is an arbitrary number, so bigger than or bigger than or equal to doesn't matter in this case. So, so this is supposed to be, according to Chebyshev's inequality, less than or equal to the variance of Yn over n divided by epsilon squared. So all we need to find is the variance of Yn over n, which we actually have already done. Okay, 1 over 4n. let's replace it here, 1 over 4n epsilon squared. So this tells me that, well, as n increases, let's take the limit as n goes to infinity, the probability that yn over n minus 0 is bigger than or equal to epsilon is less than or equal to 1 over 4n epsilon squared. Again, take the limit as n goes to infinity in both sides of the inequality. What is the limit of this? 0. In the limit, the probability is upper bounded by 0. This means, since probabilities are always non-negative, this goes to 0. So we conclude that the probability that yn over n minus 0 is bigger than or equal to epsilon for any epsilon goes to 0. So this satisfies the definition of convergence in probability. We have proved that yn over n converges in probability to 0. Okay. Are there any questions? Yes, please. What do you mean? We just tried to prove and proved that yn over n, the sequence, converges in probability to 0. Maybe it will be more concrete for you after we do a numerical example. How about that? Huh? Right. In fact, look, let's go back to the problem. Flip a fair coin n times. Independently, yn is equal to the number of heads minus n over 2. So once you flip a coin twice, yn over n is x1 plus x2 over 2. It takes the values 0 or 1/2 or 1. Consider y3. y3 takes the values 0, 1 over 2, 3, 2 over 3, and what else? Huh? Why? You throw a coin, okay? How many n times? How many heads can you get? From 0 to n, right? Now, subtract n over 2 from that. Why are we subtracting n over 2? I think that's your problem. We're subtracting n over 2 to get the mean out. Okay, so let me repeat. If you sum xi's, I from 1 to n, okay, this is the number of heads in n tosses. Agreed? Now, what is the mean of this random variable? The coin is fair. The coin is fair. So, the expectation of this is n over 2. On average, I expect n over 2 heads, right? Okay? So, the expected value of summation xi is n over 2. Now, yn is defined as this summation xi, I from 1 to n, minus n over 2. What do I achieve by taking n over 2 out? I take the mean out, so I get something that has 0 mean. Okay? So yn gives me the fluctuation around the mean. For example, consider y1. Okay? The number of tosses is 1. The number of heads can be 0 or 1. Okay? y1 takes values in minus 1/2, 1/2. Right? Let's think about y2. The number of heads in two tosses can be 0, 1, or 2. Subtract the mean, which is 2/2, which is 1. Subtract 1. I center that to be around -1, 0, 1. Okay. Let's think about y3. y3, you tell me. What are the possible values of y3? Right, 0, 1, 2, 3 are the number of possible heads. And I take out 1.5 from that. Right? 3/2. So, right, -1.5. And maybe let's just say -3/2. -3/2. minus 1/2. And then there is no 0 because if I take 1.5 out of 2, I get 1/2. 1/2, 3/2. That's it. What's happening? Again, it's centered at 0. You see? It's centered at 0. But it has some variation. It can go up to 3/2. It can go down to -3/2. Let's continue like this. I think it's fun. Let's do this. Let me make some space by erasing this part. Y4. Somebody else. Let's ask somebody else. Number of heads goes from 0 to 4. Take the mean out. Right. -2. Do you have -1? -1. 0, 1, 2. Okay. How about y5? I don't know until everybody understands what's going on. So, very nice. -5/2. Minus what? 3/2. -1/2. 1/2. 3/2. 5/2. Okay. Okay. So now, do you see? You see? I think it's we just made this yn more concrete. Yn is a random variable. It takes how many values? N plus 1 values, possible values. Okay, and its mean is 0. Now, yn does yn converge? No, it doesn't converge. It expands, right, as n increases. But the question is asking us about yn/n. Okay, so let's think yn/n in this case. y1/1. It's the same as 1. It takes these values. How about y2/2? y2/2. It takes these values. Interesting. y3/3. It takes -1/2, -1/6, 1/6, 1/2. Wow. It's still living between -1/2 to 1/2. Just like y1 and y2. How about y4? Divide by 4. y4/4. -1/2, -1/4, 0, 1/4, 1/2. It's still living between -1/2 to 1/2. So it's taking 4 possible values, but those values are squeezed between -1/2 and 1/2. Okay, and y5/5, again, -1/2, minus 3 over 10, minus 1 over 10, and etc. It goes like this. So as n grows, yn over n is taking values in this interval. Now, let's see. The question is, now let's think about the probability distribution in this interval. Okay. I claim that the probabilities of these values around the center are higher. Well, let's not go there. Think of it as a binomial. If you throw a coin n times, what is the probability that all n tosses are heads? That has low probability, right? 1/2 to the power n. On the other hand, mixtures with an equal number of heads and tails, or almost equal, are higher, more probable, because they have more ways of occurring. For what is the probability that exactly half are heads? It's again 1/2 to the power n multiplied by n choose 2. So it's n choose 2 times more probable than all of them being heads. So these values have smaller and smaller probability. These values have higher and higher probability. Okay? Now, so what's happening is as n grows, the range of this random variable, support of this random variable, yn over n, stays confined to the interval -1/2 to 1/2. Okay? And the probability gets more and more concentrated here at 0. That's exactly what we did. We proved that the probability that yn is away from 0 is very small. In fact, yn over n, is away from 0 by more than some value epsilon. Let's draw epsilon here. Suppose this is epsilon, okay? No matter how small epsilon is, the probability that yn over n is here within an epsilon interval of 0 is going to 1. The probability that yn over n is outside this epsilon window around 0 is decaying to 0. You see? This is very interesting. So this is the interesting thing about tossing a coin many times. You can get very large values, okay? But on average, the number of tosses, the number of heads will converge to 1/2. Okay, the frequency of occurrence of heads will converge to 1/2. You already knew this before you took this class. Okay, but this is the point where we mathematically understand it. Okay, we're not done with this example. The next thing, which is the weak law of large numbers, takes this example and generalizes this. Okay, so think of this as a warm-up exercise. Okay, here we just proved that using Chebyshev inequality. This is really an exercise of Chebyshev inequality. We just proved that yn over n minus 0 converges to that is yn over n converges to 0 in probability, which is equivalent to saying that yn converges in which is equivalent to saying that the sample mean 1 over n I from 1 to n xi converges in probability to 1/2. But we will do this in the next exercise. You see what I mean? I know. Okay. So, yes please.
Biz şimdi bu başlarken dedik ki işte para atınca yazı gelme ihtimal 1/2. Sonra bitince de bunu kanıtlamış mı?
What do you mean?
Ya en başta bütün işlemlere başlarken işte head gelme ihtimal 1/2 diye başladık.
Hı hı.
Sonra bir sayfa işlem yaptık. Sonuçta da head gelme ihtimal 1/2'ymiş diye bir şey deniyor.
No.
Ya da bir sürü kez para atınca yarısı head oldu. Dedik sonuçta.
Nice. More or less, that's what we said. So let's. Okay. For the moment, stop thinking about this example. Let's switch to the next one, which is maybe going to be easier to understand. So, let's see. The weak law of large numbers is one of the most important applications of convergence in probability. Okay? What are we talking about today? We're talking about convergence in probability. That's a type of convergence. We have other ways, other types of convergence, but in this class, we are just learning two. One of them is convergence in probability. The other is convergence in distribution. Okay. Now, here's the weak law of large numbers. This is really cool, something that you can apply to your actual real life. So, and answers questions like you, my friend, just had. Okay. So, the weak law of large numbers is a special case of convergence in probability. Consider x1, x2, and so on that are IID with expectations being equal to mu, variance being equal to sigma squared finite. Okay, right now we're assuming finite mean and variance. This is technical. It's not always necessary, but for the moment it's just going to make our proof easy. The sample mean sequence. In our life, we always take sample means. For example, we give an exam to 280 students, right? Like we do in this class. And then we average their grades. That's a sample mean, right? Now, we are interested in this mean. If, for example, I toss a coin 500 times, just like you asked, right? 500 times. Will the average number of successes per toss converge to 1/2? And how when will it converge, for example? That's an interesting question. Does increasing the number of tosses from 500 to 600 change the result a lot, for example? That's an interesting question, although we're not going to answer it now. We'll just show the convergence result itself. Okay. Now, obviously, when you toss a coin 2 times, you expect, and you toss a coin 2 times, okay, and average the number of heads, you expect some variation. The average, may be different from 1/2. What is the average going to be? 0 or 1/2 or 1. Okay, and the probabilities of these values are appreciable. On the other hand, when you toss a coin 500 times, okay, the average becomes more and more likely to be around 1/2. Okay, you see what I mean? Okay, right now we're trying to make this precise. So take this sample mean sequence, Mn, which is 1/n summation xi. I from 1 to n. This is the sample mean. This is the sample mean. Okay? Now, what do we have? We have that the probability that mn minus the expectation of mn is bigger than epsilon, okay, or bigger than or equal to epsilon, is upper bounded by what? From the Chebyshev inequality, it's upper bounded by, from this Chebyshev inequality, okay, the variance of mn minus expectation of mn, if you want, divided by epsilon squared. Any problem with this? Any problem? This is a random variable minus its mean. Variance of mn minus expectation of mn is the same as the variance of mn. Right? Now, so what do we need? We need the variance of mn, variance of m sub n. What is that? That is 1 over n squared times n times the variance of xi, if you want, for all I. Or replace this by 1. Why? Because the xi's are independent. The only reason why this is working is we are adding independent trials. If the trials were dependent, then we would not get such a convergence result necessarily. Okay? So this is variance of x1 divided by n, and the variance of x1 is given to be, let's see, it's given to be sigma squared over n. Okay? So we just have that this is less than or equal to sigma squared over n, which goes to 0 as n increases. Okay? So we say that the sample mean m sub n converges to the expectation in probability. What is the expectation? Expected value of m sub n is 1 over n times expected xi, which is mu. Okay? So the sample mean converges to the mean of the xi's in probability. So this tells me that if I take a large number of independent samples and I average them, I should find the expectation. This can be thought of as a link between statistics and probability, for example. In statistics, we take sample averages. This tells me that the sample average converges to the true mean. Okay? This is called the weak law of large numbers. Law of large numbers. Law of averages, sometimes it's called in daily life. Right? Okay? So, in what sense does it converge? It converges in probability. Okay. Is everybody clear on how we use Chebyshev's inequality on this example?
Sigma square over n zeroya yaklaşmasını kullandık mı bizim?
Right. Sigma square n appeared here.
Yani mü'ye konverj ederken onu nerede kullandık?
Okay. The probability that mn is away from mu is this. it's upper bounded by sigma squared over n. Okay? And this goes to 0. So this means the probability goes to 0. Okay? Please ask me if you have any questions. Okay, the classical example. I think you have a question. Okay. So let's rephrase this problem in the language of the previous example. Okay. In the language of the previous example, xi are the number of heads. Okay. So m sub n is the average number of heads in n tosses. What is the expectation of xi? What is mu? Mu is the expectation of xi. So in this example, mu is 1/2. Right? Mu is 1/2. So the average number of heads per toss, mn, converges in probability to 1/2. You see? Okay. The canonical example for applying this result is in voting, okay, or in polling. You poll people, you make an opinion poll and ask a binary question, for example, a yes or no question. Will you vote for XYZ or do you vote against XYZ? Okay, replace your favorite issue in place of XYZ. Okay, so why do we poll people? What's the point? Huh? Excuse me? To get an idea of the average opinion of the public, right? That's the only reason we poll. Otherwise, right. So underlying this whole idea of polling is that if we poll enough people, if we ask enough people and average their answer, the result that we get is going to be a good representative of the whole fraction of population that will vote for this issue, right? That's the idea behind polling. Okay, so let's address that question. We want to estimate the fraction of the population that will vote for XYZ. Let xi be equal to 1 if person I votes in favor of XYZ and 0 otherwise. Okay? So how many people should we poll to make sure our error is less than 0.01 with 95% probability? Okay, so behind this idea, behind this question, there's the idea that people's opinions are independent of each other. So, in a good poll that will work, you should ensure that the person that you select are reasonably independent of each other. So, for example, if you want the opinion of the average opinion of the general public, you should really go and interview people from a lot of different groups. Okay, if you kind of, for example, if you want the general opinion of the public and you only go and interview males that are between 20 and 25 years old, okay, that's not likely to give you the average opinion of the public, right? Because that's a certain group, and people in that group may have certain similar ideas, perhaps. Okay? So suppose we are able to find n people whose opinions are independent. Okay? So that's the assumption. Suppose we poll, that is, poll n people who have independent opinions about issue XYZ. Okay? And we further model this opinion as random, such that a person will either vote yes or no. Okay? So xi is either 1 or 0. But the probability that any given person, arbitrarily selected from the population, votes in favor is p. This is our model. This is our model. No one can argue whether this is true or not because it's just a model. Okay? This is important. If we believe this model, then we can go on and solve this problem as a probability problem. Okay, so let's see. I don't need to erase this next one because that sample mean is exactly what we will do. So when you poll people, what is the outcome of the survey? What is the outcome of the opinion poll? Okay, outcome of the poll is the fraction of people who voted yes or who voted for this issue. So let's call that Pn hat. Okay, fraction of people among the population that you've polled who voted for XYZ. Okay, so then the fraction P and star is nothing but the sample average of Xi's. Okay, that's nothing but the sample average of Xi's. Okay, what do we know about this fraction, about this sample average? Remember, the Xi's are IID with expectation equal to P, and the variance is P times 1 minus P. Why? They are Bernoulli random variables. So, by the weak law of large numbers, this is important. We are now applying the weak law of large numbers because we already proved it. The fraction Pn hat converges to the true probability P in the sense of convergence in probability. Okay? So we know that if we poll an arbitrarily in a larger and larger group, eventually our estimates will converge to the true probability P. Okay? No problem here, I suppose. So we'll finish this example and then give a break after that. Okay? So now, here's the question in the problem. The question in the problem is, how many people should we poll to make sure the error is less than 0.01 with probability more than 95%? What is the error? The error after polling n people is the difference of Pn hat and P. Okay? In absolute value. Okay? How much we differ from P. Okay. Now, what is the probability that Pn hat minus p is less than 0.01. Do you know a way of upper bounding this? Are you okay? Huh? Chebyshev inequality, right? Chebyshev's inequality. So why is Chebyshev's inequality useful here? Because P happens to be the expectation of Pn hat, right? Expected value of Pn hat is P. Okay? So the probability that Pn minus expectation is less than or less than this number, or again, let's use it with less than or equal. Let's use it with this. Is bigger than or equal to this number, is less than or equal to the variance of Pn hat divided by 0.01 squared by Chebyshev's inequality. Okay? So, what is the variance of Pn hat? Variance of Pn hat is, let's compute it here, variance of Pn hat is 1 over n squared times n times variance of xi, which is 1 over n times p1 minus p. Okay? So this is p1 minus p divided by n times 0.01 squared. So we're almost there. We're almost there. We have upper bounded the probability of our error being bigger than or equal to 0.01. Okay? So we're interested in the probability that our error is less than 0.01. Okay? Our error is less than 0.01 is 1 minus this. It's lower bounded by 1 minus this. P times 1 minus p divided by n times 10 to the minus 4. This is a very important step. Now tell me how big n should be. Let's first look at here. As n grows, okay, as n grows, this number goes to 0. So this right-hand side goes to 1. Okay? The probability that our error is sufficiently small goes to 1, which is great, which is as we expect. However, what is the smallest value of n such that this will be desirably small? Okay? So we want this, we desire this to be bigger than what? 95%. Because this is the probability that our error is within this bound. This is the probability that our error is less than 0.01. We want that probability to be at least 95%. Okay? So if...
%1'den düşük olunca zaten %95'in üstünde olmuyor mu? %1'den düşük olunca hata.
No, the error is random. The error is a random variable, right? So there is a probability that the error is less than 0.01. We want that probability to be upper bounded by 95%. Okay, that's the idea. Now, so if we make the right-hand side to be 95% or 0.95, we're done, right? The probability that the error is less than 0.01 is at least this. So if we make this 0.95, we're done. What is the value of n that will make this 0.95? That n should make this part equal to 0.05. Okay? So what is the value of n? What is the right value of n? There is one problem. We don't know p. But we know the worst case for p times 1 minus p. The worst case, the largest value that that can take, is 1 over 4. So, worst case, p is 1/2. And in that case, if we set 1 over 4 divided by n times 10 to the minus 4 to be equal to 0.05, we're done. Okay? This will be, this will be sufficient. So this tells us that n is at least, so let me erase this part. So n is bigger than or equal to 0.05 times, and is at least 1 over 4 divided by 0.05 times 10 to the minus 4, right? Right? Which is what? 50,000, right? Because, right, this is 50,000. Okay? So so basically, n equals 50,000 guarantees that the probability that the error is less than 0.01 is bigger than 0.95. Okay? So this is the end of this example of using weak law of large numbers. The nice thing is, right now this looks very big, but this gives us an absolute guarantee. Huh? So 50,000 people, interviewing 50,000 people is guaranteed to be enough to satisfy our error requirement. But this is sort of too much, and we'll find out in the next hour, after we prove the central limit theorem, that by applying the central limit theorem, much fewer people will be enough to get this error rate. Okay?